Hello Stat students. Today we're going to look at another probability distribution called the geometric probability distribution. Not as important as the binomial, but occasionally you do see questions about it. And it's much easier to understand than the binomial distribution. Let's start off with an example question. Suppose 8% of people are left-handed, and you're going to just keep selecting people until you get a left-hander. Just keep drawing randomly over and over and over again until we get a lefty. So let's ask a simple question. What's the probability the first lefty is the first person? You get lucky and the first person is a lefty. That's not difficult. The probability of a lefty is 8%. So that's just 0.08. What's the probability that your first lefty is the second person? Now, that's a little bit trickier, but not too bad. Since there's an 8% chance of getting a lefty, there's a 92% chance that we don't get a lefty. So for the first lefty to be the second person, we have to get a right-handed person and then a left-handed person. And so that's 0.92 times 0.08. And what about if I say the third? What's the probability the first lefty is the third person? So again, this is, we need a right-handed person, then a right-handed person, then a left-handed person. So that's 0.92 squared times 0.08. And you can see the pattern here. So let me define this random variable that has a geometric probability distribution. Let x be the number of people drawn until we get a lefty. And notice that we're talking here about wait time, and that's the sign that you'll probably be using a geometric probability distribution, is that if you're looking at a wait time question, how long until we get something, as opposed to binomial, which was how many successes. We were measuring something entirely different. We were counting successes. Here we're just waiting for a success. We want to know how long. We can make a table for this binomial, or for this variable x, and you'll notice that this has a property we haven't seen yet, is that there's an infinite number of different values that x could have. We might get the lefty the first time, the second time, the third time, the fourth time, the fifth time, etc. So this goes on and on and on and on. Okay? And the values over here are just the values we've already seen. First person is a lefty, 8% chance. If we have to wait for 2, that's 0.92 times 0.08. If we have to wait for 3, that's 0.92 squared times 0.08. If we have to wait 4, 0.92 cubed times 0.08, because we have to have 3 right-handers than the left-handers, etc., etc., etc. It just keeps going right on down the list. It's very straightforward. These are easy probabilities to compute because there's only one way each of these results can happen. If I want to wait if I want to see what's the probability of the first lefty, say the 10th person, that means there's one way for that to happen. I get 9 right-handers and then I get a left-hander the 10th time. So this is an example of the geometric probability distribution. And we're just going to get the general formula here. If p, probability of success, is replaced with lowercase p, let's look at the table, and it's exactly what you'd think. If we're replacing 0.08, the 8% here, with just p, so then here this gets changed into p, and then if I want this first success to happen on the second attempt, that means I need a failure, then a success. So that's 1 minus p, that's the probability of failure, times p, that's the probability of success. I don't want to keep writing 1 minus p or 1 minus p, so I'm going to do what is often done, is we're going to write q for 1 minus p as a shorthand. So what's the chance the first success is on the third? Then I would need 2 failures, then a success. That's q squared p. The first success is on the fourth. That would be q cubed p. First success on the fifth, q to the fourth p, and so on and so on and so on. This continues on and on and on. Hopefully this is straightforward. A little bit trickier is the next thing I want to look at. What is the mean and the standard deviation of this distribution? And again, let me lead off with a question. Let's say you roll a die until you get a 6. On average, how long will you have to wait until you get that 6? Notice that this is geometric again. We're asking about a wait time. We're waiting for our first success. Success is a 6, and I'm asking how long do I have to wait. Now here it's the mean. On average, how long will I wait? We're not computing a particular probability. You probably would guess 6 rolls. Since there's a 1 in 6 chance of getting a 6, you say, well, probably on average you'd have to wait 6 rolls. You might get it on the first, you might get the first one on the 10th, but on average 6. And that's actually correct. Your intuition is correct. So what I want to do is, I want to use my geometric probability distribution to prove this general formula that the mean wait time is 1 over p, 1 over the probability of success, or the reciprocal of the probability of success. That's what we were saying here. There's a 1 in 6 chance of getting a 6, so on average it would take 6 rolls. If we had some other thing that had a 1 in 10 chance of success, we would expect to have to wait on average 10 attempts until we got our very first success. If something had only a 1 in 100 chance of succeeding, we'd expect to wait 100 times until we get our first success. Now that's on average how long we'd have to wait. We might get our first success the 4th time, or it might take 250 trials. But on average, it would take, 1 over p, where p is the probability of success. I want to prove this formula. It's some nice algebra in proving it. So here is my table again. I copied it from the last slide for the geometric probability distribution. Probability of the first success is on the first trial, second trial, third trial, fourth trial, fifth trial, so on and so forth. I want the mean of this probability distribution. And if you remember back, the way we compute the mean is we multiply the value times the probability, and we add all those up. So we have 1 times p plus 2 times qp plus 3 times q squared p, and so on and so forth. But we run into a problem. This is an infinite sum. We want to add this up, and we have what's an infinite series. So I'm going to use a clever technique, and it's going to have at its core something you learned in pre-calculus last year, which is the sum of a geometric series. So 1 plus r squared plus r cubed plus r to the 4th, so on and so forth. You may or may not remember that this adds up to 1 over 1 minus r. I'm going to need this fact in my proof. This is not exactly this here because of the 2 and the 3 and the 4 and the 5. That is not stepping up by powers of anything. It's just adding one. So I have to do some manipulation first before this formula will be useful. And this is just a really sneaky technique, and it's not something I came up with. I read it out of the book. What I'm going to do is I'm going to take my equation here for the mean. I'm going to multiply both sides by q. So on the left-hand side, I'll have q times mu x. And what will happen over here? Well, the q will distribute onto each of these. So instead of 1p, I will have 1p. Oops, okay, I rewrote it first. Right. Okay. Instead of 1p, I'll have 1qp. And then the q distributes onto here, and I get q squared. And the q distributes on the next one, and I get q cubed. And then I will get q to the 4th. And then I'll get q to the 5th. And so on and so forth. What good does that do? Well, notice that this qp is a like term with this. This is a qp term. This q squared p term is also q squared p term for that. So I'm going to rewrite these series. There's the first one, and here's the second one. But I'm going to move these terms over so they line up with the like terms from the previous one. Do you see that? Hopefully you see that. I know I'm asking you a question. You can't answer me. Hopefully you see that. All I've done is I've shifted this over so the like terms add up so that I can subtract them. So if I subtract the left side, I have mu x minus q mu x. So that's 1 mu x minus q mu x. So it leaves me with 1 minus q mu x's. And then here I have like terms. So I have nothing that's like term with the p, so I just get p. Then I have 2qp minus 1qp. That's 1qp. Then I have 3q squared p minus 2q squared p. That's 1q squared p. And you can see what's going to happen here. q cubed p, q to the 4th p. We got 4 minus 3, 5 minus 4, so on and so forth. So when I subtract, I get this. And I have a factor here of p now. There's a p on every term that I'm going to factor out. And what's left is exactly a geometric series like this one, where r has been replaced with q. So using this formula from pre-calculus, that sum is 1 over 1 minus q. So, but now I have to remember, wait, q was the probability of failure, and P is the probability of success. So that means P plus Q is 1. So this 1 minus Q here is actually equal to P. I just look at this equation. Q is 1 minus P. So looking at this here and this here, I can replace 1 minus Q here and on the other side with P, and I get P mu x equals P times 1 over P, and I divide the P's away and I get my goal. The mean of the geometric probability distribution is 1 over P, which is what we intuitively guessed when we asked the question up here. 1 in 6 chance of success means I'd have to wait on average 6 rolls. You also need to know the standard deviation formula. I'm not going to go through the proof of that, but you should memorize it. The standard deviation of the geometric probability distribution, blah, 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 is square root of Q over P, where again Q is 1 minus P. Okay, so now I have some problems I would like you to try. You try it. So I'll pause this here for you to try these problems. Okay, here are my solutions without any explanation. So I'll let you look these over. You can pause this and study and discuss these solutions. I hope you learned something, and I'll see you soon. Bye-bye.